Alrighty guys, so actually, people, I should say. Okay, yeah, that's good. Okay, so I have the notepad up here. Let me go ahead and type out the stuff so it's a little more visible and clearly written. So today is the 15th, July 14. Our objective today is to, anyone know the shortcut for putting bullets up there?
Alt F4.
Oh, no, come on. Jerk.
Turn it out spare play. He tried that on me the other day.
Okay, so the primary thing we're going to do today is go through and define the cyclic coordinate descent algorithm. What we're wanting to do, and I have the two-link example that I started on yesterday put together for you, so let me open it up. I spent most of the morning without access to the network drive because for some reason it was not available. So let's see, this is problem number 12. And when I run this, what we're going to see is that the robot is assigned an initial joint position initially. And then we're going to select a destination, so anywhere within the workspace. If you want to do one extra little bit on the program, which isn't specified, you could go through and plot a big old circle representing what the workspace looks like. That way when you're clicking around on the plot area, you're not unintentionally clicking outside of the workspace and resulting in a no solution type of scenario. That's something that I actually included in this assignment the last time I taught the class, but it's not something that I'm going to expect of you. It's just kind of a handy thing. So in this case, I'm going to select this as my destination. As soon as I click this, the robot is going to rotate around, starting with the last joint, and try to reach that destination. Okay? You'll notice that there is a slight variation here. What does that mean? If you look closely here, you can see that the end of the end effector is right here where my mouse pointer is, and the destination was here. For troubleshooting purposes, what I did was I set my tolerance to 1/2. Just so that it's close enough so I can see if it's working, but it's still large enough so it's not going to go through a ridiculous number of iterations. You notice something here, something else. What can we probably say with the motion across an existing link when we're dealing with a physical robot?
Well, you're probably not going to be able to. Can you cross over the other link?
Generally not. Usually when we're defining these links or building the physical robot, we're restricted to a angle of rotation that does not allow rotation over an existing link. Does that matter so much for the CCD algorithm? The CCD algorithm would be implemented internal to the robot. So the robot would go through when it needs to achieve a destination. It would run this algorithm internal to the robot in order to figure out the set of joints necessary to achieve that end position. And once it has those joint angles, then it would just go out and move the robot. So even though we're showing this motion on the plot area here, the robot would never actually make or perform these sequence of motions in order to get there. This is all just the algorithm that goes into selecting those joint positions, not necessarily the physical motion of the robot. So I'll do this again, just be because you know me, I like doing stuff 3 or 4 times. So I don't know, what do you think up here? So we're going to go through, and sure enough, we land on the destination. So with that being said then, we're going to go through and define the cyclic coordinate descent algorithm. And before we get there, of course, we have our warm-up, which was up on the piece of scrap paper a second ago. We're going to go through and determine a set of joint angles needed to place an vector at 10, 10 if each link is 12 units long. Okay, so I'll give you a minute or so to go through and do this. Once you have had a minute or so, we'll go through and describe this in class. And then we'll buzz on with our introduction of the CCD algorithm. It's really kind of cool. The simple example that I produce, of course, only has 2 joints. The problem for this week will be that same algorithm, just applied to a larger number of joints. And you'll see from the pseudocode that we developed today that we can do this for who cares how many joints. It's the exact same algorithm. All you have to do is increase the number of DH parameters that you pass into it. Anyone want to be a movie star? Dang it. I'll just stay hidden up here away from the camera when I go through the solution here, so. By the way, the example code will not be available until next week, because if I give you the example code for the 2-link, then it's really quite the trivial exercise to actually develop this algorithm on your own. So I'll be providing you the pseudocode, and from that pseudocode you should have enough background to develop the algorithm itself. And of course, we're going to have tomorrow and Thursday to work in class on this. So for those of you that are not in class, this will be a very easy program to get stuck on. So I would suggest that if at all possible, you try to make it to the lab sections over the next couple days. So. So we have this destination point here, and actually let me redraw that so it's not sitting right there on top of the graph. I, of course, did not bring my scale today, so so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the point we're trying to achieve is that point right there, and we know that we have 2 segments to get there from the origin. Both of those segments are 12 units long. So what's one thing that we can do right away?
Can we just lay one flat across the x-axis?
We could, but if we do that, you'll see that that would put our first segment right here, 12, 0, and with that there, what's the distance from here to here? So the distance then would be the square root of 12 minus 10 squared plus, let's see, the change in the other thing, change in y then is 0 to negative 10, or 0 to 10. So then we have the square root of 12 minus 10, which is 2 squared, or 4, plus the square root, plus 0 minus 10 squared, which is 100. And I may not know what the square root of 104 is, but I know what it is not.
12.
It is not 12. So can we in fact lay that first segment on the horizontal axis as we did? Now, in this case, we see that since this is less than 12, we're going to probably have to, at least for one of our 2 solutions, adjust that joint down into the 4th quadrant. Okay? And from there then, we should be able to find an angle here that allows us to measure that distance up to the destination of 12. Good. Okay, so one way that we can work with this is we can just draw the position vector out to that point. So if we go through and draw the position vector out to that point, what does that allow us to do? Well, now we've got a triangle, don't we? And I don't care what kind of triangle you have, any triangle can be redrawn as 2 right triangles. Okay? In this case, I'm going to go through and draw my altitude to that position vector, because we know that that position vector is going to be sitting there at a right angle. Okay? Now, how does this help us?
We can determine our link angles now.
Okay, we know the link angles are, the link lengths are 12, and since we can calculate the length of this side, sure enough, we can go through and calculate the angle here, and, well, all of the interior angles, just applying our basic trig properties. Okay, so with that, let's go ahead and do that. First off, what is the length of the position vector pointing out to that point? By the way, this is particularly valuable for you heading into statics this fall. You're going to be resolving a lot of stuff this way, so. Are you taking it from Pringle or from Wayland? Or do you?
Not Pringle.
What?
Not Pringle, I know that.
Okay, so probably Wayland. He's old school. Take that any way you want it, so. Okay, so in this case, if we go through, we can say that, well, this is a position 10, 10, so I know just from my 45-45-90 theorem that the length of this position vector is going to be 10 times square root of 2, which is 14.14 units long. Since this altitude is going to bisect that position vector, we can say that this segment is going to have a length of, I guess I need 2 tags there because I already used a single tag here to represent that segment. Going to have a length of 7.07 and length here of 7.07 for a total length of the 14.14. Aren't you glad you're not going to see this on an exam? This would be one of those problems that would be pretty easy to, go sideways on and not have a real good solution by the time you ran out of time. So with this said then, now we can go through and figure out what this angle is. Okay, so we can say that the arc tangent here, I'm sorry, not the arc tangent. I suppose we could use arc tangent, but that'd be a little more work. The arc cosine is going to equal our adjacent side to our hypotenuse. Or rather, we're going to evaluate the arc cosine on the adjacent side to the hypotenuse. And when we do so, what does that angle turn out to be?
53.9 degrees.
53.93 degrees. Okay, how's that help us?
We can find our top angle now.
Okay, we can definitely find our top angle.
Well,
This is an
The
isosceles.
other angle, the one that we really want,
Which one's that?
the one at the bottom.
That angle there, isn't it? How can we find that angle?
Subtract 45 degrees.
Subtract 45 degrees, because we know that this is a 45-45-90 triangle. Therefore, this interior angle here is 45 degrees. The total angle is 53.93 degrees. Therefore, this angle is nothing more than the 53.93 minus 45, which is 8.93 degrees. In fact, it would be a negative 8.93 degrees. That makes sense? And that's only if I, rely on my shoddy skills here, so minus 45, yes. Okay, wanted to make sure that I performed simple subtraction correctly. Okay, so we now have an angle of negative 8.93 degrees. That means that we can now determine that position. That position then would be 12 cosine of negative 8.93 degrees and 12 sine of negative 8.93 degrees. So what is 12 cosine of negative? It's going to be 11 something. I got 11.8. So,
I got 1.8.
what's that?
So I got 1.8. I'm not sure why. Oh, I did sign, sorry.
Yeah, I bet you did sign there, so 0.8 and 1.8. In fact, we know it's going to be a negative. Let me just punch it in here. So, negative. Yeah, negative 1.8. I actually got 1.85, so we probably should round that to 1.9, but I suppose if we developed any kind of significant figures convention, we'd probably have to stick with 3 significant figures since that's what we specified the angle in. Okay, so with this then, we've got the position, and now we can check the distance just by going through and applying the distance formula again to make sure that that's valid. But more importantly, how are we going to determine that second joint angle? These are kind of like those really irritating geometry problems that you ran into back in high school. Just never seemed, at least to me, as if they provided enough information for them, so. Well, I think it's going to be 106, well actually 107, and a little bit of change, probably quite a bit of change actually. What is that, 0.86, so 107.86 degrees, okay? Because what I said was, okay, well this interior angle is 53.93 degrees, therefore this exterior angle is going to be twice that. And let's just see if I'm correct. If we go through and find the tangent of this angle here, theta, we can say that that's equal to, what's tangent equal to? Change in y's over change in x's. So in this case, we can see that the change in y is going from, let's see, 10 down to a negative 1.9, and the change in x's is going from a 10 to a negative 11.8. So that means that our theta angle is going to be the arctangent of this value, so that's 11.9 over a negative, what would that be, 1.8. So the arctangent of 11.9 minus divided by negative 1.8, and I get a negative 81.3, well, 81.4 degrees. What is the interval of existence on the tangent, or I'm sorry, the arctangent though? It's defined from negative 90 to positive 90, isn't it? Therefore, what would we have to do to actually see if that's correct? Or in order to convert that to the proper angle that we're looking for. So we know that the tangent value we just found is sitting right over here at negative 81. We would have to shift it over to here, which would add 180 degrees to that. So plus 180 degrees to put it where we're wanting. And actually I got a 98.6 degree angle for some reason. So maybe this hypothesis isn't quite correct. But does that kind of make sense to what we're doing there? So it looks like our initial joint angle is going to be a negative 8.93 degrees, and our second joint angle is going to be the 98.6 degrees. Good. Fortunately, we don't need to do this because we will have the CCD algorithm available to us after today. This would become a very tedious. How many of you have read chapter 4? If you do, it becomes particularly irritating after you exceed 2 joints, because they don't necessarily just go out and arbitrarily pick a joint angle for the first one, for one of the joints. They go through and say, okay, well, this joint can be this, and essentially they work backwards through the chain in order to figure out what all of the particular solutions can be. So it tends to be a very cumbersome process if you approach these inverse kinematics using your trig properties that you already know. Okay. For 2 links, it's really not that bad. It does get kind of irritating depending on the orientation and the destination, but overall it's not too bad. So, but when you get up to 3 links, and hopefully you never have to deal with 4 links and so on and so forth, it becomes particularly challenging. You move on into 3 dimensions and start considering your orientation, then this simply is not something that you're going to try to ever do by hand. So, good. Okay, so let's go ahead and take a look at this CCD algorithm then. As we've already said, the cyclic coordinate descent algorithm determines the set of joint angles needed to reach a destination by incrementing through each joint until n is putting at at the end of the sentence is a bad thing to do, isn't it? I could probably go in and try to rephrase the sentence, but I won't, so. Okay, so what are we going to do then when we're developing this algorithm? And I'm going to go through and type this up as pseudocode so that we kind of have a framework for your assignment this week. Okay? So what's the first thing we're probably going to do, even though this isn't necessarily part of the pseudocode itself, or a part of the CCD algorithm itself. Got to start with the description of the robot, right, of the manipulator. So we're going to specify the DH parameters for a manipulator. And any variables. Well, I shouldn't call them variables, I should say any constants. Okay, one of these constants that you'll definitely want to specify is your tolerance. And I'm not going to specify a tolerance, but a good place to start is to, when you start working with this algorithm, that's close enough so that you'll be able to clearly see if the robot or if the algorithm is working, but it's not so tight so that it'll spend forever to reach that destination. For your final tolerance, you should be 0.01 or less, okay? So you want to make sure that when you get to the point where you know that your algorithm is working, that you really pull that tolerance in. That way you don't need to worry about having, just approximate solutions. I suppose, given that this is a numerical process, the only thing we will end up with is approximate solutions, but we want to make sure that that approximation is as accurate as possible. That makes sense? Let's real quick consider the difference between tolerance of 0.5 as we have here. Let me find my tolerance. I have a tolerance of 0.5 here, and I will just select a point, okay? And I will repeat that with a tolerance of 0.01. Okay, what do you notice? It hasn't yet achieved that solution, has it? It's still sitting there iterating back and forth. Part of the reason for this is because I have my joint angle incrementing at 2 degrees per step. And that's kind of a bad thing because if we increase tighten our tolerance in, well, that new tolerance value may not be achievable given the increments that we're stepping in. So, let me bring up my command window and I'll break out of this. In fact, you can see here that I'm just never getting within that range that I'm looking for. So I will go in and change my joint angle to, say, 0.5, and now rerun it. And of course it's going to take longer just because we're working with smaller angle increments. But once it does get down to the point where it's close to the approximation, you can see that it's taking quite a while. Even a ½ degree increments is apparently too much. I'm doing Control-C to break out of the window here. So we'll try, say, 0.05 degree increments. Maybe 0.01 is really not achievable. Because of course it's going to take forever to get there.
So windshield wiper.
What's that?
I was just making a joke. I said it's a windshield wiper.
Oh yeah, I know. It's that'd be kind of fun. You could sit there and make a windshield wiper simulator. Okay, so I'm thinking that the 0.01 tolerance probably isn't going to be for us. How about we shoot for a tolerance of 0.1 instead of 0.01? Just so that we don't have to make a curve out of this. So I will go up and change this to 0.5, change my tolerance to 0.1, and close this, rerun it. The entire point of this example is to demonstrate that it does in fact take longer to arrive at your solution when you have a tighter tolerance. And we can definitely see that's the case, okay? Okay, so we've got that. So next thing we're probably going to want to do is go through and configure the plot area this is something we've already been doing. Keep in mind that we're probably going to want to make sure that our plot area is capable of fully representing the range of motion available on or within our workspace. In our case, our total, let's see, wasn't our maximum reach 105 units? If I recall, that's what we defined our maximum reach as. That means that your workspace or your plot area should, maybe be positive and negative 110 in the X and Y direction. Now, there is something that you can keep in mind here. Since we're simulating the CCD algorithm on a two-dimensional plot, we don't need to use the 3D plotting utility. We can just use the standard 2D plot instruction instead, and that'll work for all of our everything that we're doing. That has the additional benefit that then you don't have to define a viewpoint. It's assumed to be viewed from above the XY plane. That makes sense? Next thing we're going to do is draw the initial manipulator configuration. I'll buzz on through next couple things. Okay. So we're going to draw the initial manipulator configuration. This is exactly what we've done repeatedly up till now. We're going to use the same template that we've already worked with. In fact, a good place to start would be just take the code from yesterday's lecture notes. Start from there because that already has the template set up. You can use that to build from to work around or to develop this CCD algorithm. After we do that, we're going to go through and determine the or specify the destination, and keep in mind that this is done by using the G input command. You have to specify the X destination and the Y destination as part of a vector, and specify the number of times you're going to record the input. And after you do that, you're going to determine the distance to destination. So okay. So that distance to destination is what's going to be controlling the entire algorithm. And once we know that distance to destination, we're ready to formally start working with the CCD algorithm. Because what the CCD algorithm does is it just goes through repetitive loops to minimize that distance to destination. It's going to measure the distance from the end effector to where it wants to go over and over again, and continue to adjust each joint until that distance is minimized. That makes sense? So what we're going to do first is we're going to, different color font. We're going to use a loop to continue adjusting the joint angles until within the tolerance. Okay, so this is going to look something like this. We're going to say that while the distance, and feel free to use different variable names. This is already included in the notes so that you can refer back to it if you want. So while the distance destination is greater than the tolerance, you're going to go through and continue to search for the joints that you need, the joint angles that you need. Good. And that should not be a capital, so we can thank Word for that. When we enter this loop for the first time, we're going to start searching at the very last joint. So, I'll say start by adjusting last joint. Okay. So in order to do this, what I'm going to do is set up a inside for loop. You can in fact use a while structure as well if you want, but what I did was I used two nested for loops, and I said that this for loop is starting from the last joint and going to the first joint in increments of 1, or rather decrements of 1. It would be increments of -1. Now the last joint is going to be something you're going to have to define, and this is going to be a number associated with your DH parameters. In fact, the value that last joint will contain will be the number of columns in your DH parameter list, because each one of those columns represents a joint. And actually it's going to be the number of columns minus 1, because we know we're not adjusting the final frame attached to the end of method, right? Okay, after we do that, then we're going to use that to sequentially move through the joints. And I'm going to use a second for loop in black. So for n, this is going to start at the value of m and go to the last joint in the list. Okay, so what we're going to do is, let's say that this is the first time we're moving through it. The first time we go through this entire process, we're only going to adjust the last joint and then take our measurement calculation. Okay. The next time through this, we're going to start at the previous joint and then adjust the second joint, or the last joint, in order to minimize that distance. The third time through, we're going to start with the third joint from the end, adjust it, move to the second joint from the end, adjust it, and then adjust the last joint. Fourth time through, we're going to start with the fourth joint from the end, adjust it to minimize the distance, move to the third joint from the end, minimize distance, and so on and so forth. So while we're starting with that last joint, we're progressively working up the chain to minimize the distance. At any time here, if we achieve that destination, we want to be able to break out of this loop and say, we're done. Make sense? Okay, also since this is incrementing, we don't necessarily have to state that it's incrementing by 1, but we can if you want. So we could say that our inside for loop is assigning in the values from whatever the outside loop currently is to the maximum number. And this last joint variable that I'm setting here, you can either define it as number of columns in your DH parameters list -1, or you can just say it's 5. I think it's 5. In fact, I'm pretty sure it's 5 in your case. So it doesn't necessarily have to be a variable or a constant that you assign. Okay, so after we are in the inside loop, there's only a couple things we're going to do. We're going to be sitting there searching for that parameter, or searching for the joint angle that minimizes that distance. But what are we going to have to do before we start searching? Let's say we're sitting there on the last joint and we just start rotating. Okay, we're adjusting that joint to change the direction that the end effector is facing. Okay, what if the position is here, but the end effector starts rotating away from it? That's not going to be minimizing the distance, it's going to be increasing the distance. So the first thing that we're going to have to do inside this inner loop is determine the appropriate direction of rotation. And for me, this was a very low-tech process. What I did was I just went through and made a very small adjustment on that joint to see if I increase the distance or decrease the distance. Okay? If it's increasing the distance, then that's the wrong direction. Okay? With that then, what I did was I just said that if it is larger than, or if the direction is increasing, then my rotation is negative, or needs to go the other direction. And if it was going in the right direction, I said rotation equals +1. Because what I then did was I just started incrementing around the loop and used that as my multiplier to represent if it's a clockwise or counterclockwise rotation. That makes sense? Notice that that's only going to be done one time each time we enter this inside loop. We can go in and check that direction of travel the first time we enter that loop, and that's it. We don't have to mess with it again, because everything else is going to take place within our adjusting loop. So what we're going to do is, after we know the direction of travel, adjust the end joint angle to minimize the distance. Okay, and this is going to be, or I set this up as a while loop. So what I did was I said that while the distance to destination to destination is decreasing, but greater than the tolerance, keep on looking for it. And really, really recognize here that if you type this into MATLAB, it will absolutely have a fit. So this is very, very loose pseudocode here. Okay, once we're inside this loop, we're going to do a couple of things. We're going to, well, I'll go ahead and put this inside the loop because that's where the actual adjustment is taking place. we're going to calculate frame locations. And plot the manipulator. And then we're going to go through and calculate the new distance. And how many of you remember the swapping algorithms that you probably ran into in your CS classes? So a swapping algorithm essentially changes two values around, okay? In this case, you might want to consider looking at a swapping algorithm of some place or of some form so that you can keep track of the new distance to destination and the previous distance to destination. Does that make sense? Because you're going to have to know how far you were and how far you are in order to calculate the new distance or to see if you're at a minimum. As long as your new distance is less than your old distance, then you're good to go. But as soon as it starts increasing, you know you've gone too far. That makes sense? So after we're done with that, we are done altogether. Now we just end everything and stick a fork in it. We end the while loop. We end the for loop, and this is absolutely miserable typing in. Then we end the outside for loop, and we end the outside while loop, and we're done. Now I'm going to tell you straight away that this required 5 or 6 lines of code. This required quite a bit, okay? Partly because I did not proceduralize the plotting of the data. What I did was, when I initially plotted it up above, I went and just took that section of code, followed my habits of sloppy programming and copied it into here. If you go through and create a function that goes out and plots your link configuration, that's perfect. It's really going to condense your function. But in my case, I ended up with 3 pages of code, whereas I'm sure you could do it in a page and a half or less. So are there any real, that's beautiful having an instructor ask you if there's any real questions. Any questions?
There will be.
Oh, yeah, absolutely. I mean, that's the thing. I mean, you're not going to have the questions until you start into this, right? So I fully am anticipating tomorrow you guys will just be getting your feet under you. I'm going to kind of let you, spin your wheels and think about how to get this together and stuff. And then on Thursday, when you come back in, you will be able, I'll be a little more forthcoming with, help and so on and so forth. So how's that sound? This outline will be posted on Canvas, just like usual. So you'll at least have the basic flow of the program sitting there. In fact, all you really have to do with this basic template is make sure that you define these variables appropriately in order to, so that they're used in your program right. So, good? Alrighty, any questions? Okay, so the assignment will be posted. The second part of the assignment will be nothing more than taking the joint parameters that you came up with here and then plotting motion from the original to the final. So one thing I'll say with that is you're going to want to preserve your initial DH parameters and produce a destination set of DH parameters. Because then you're just going to start with the first configuration and move to the second configuration. Make sense? Okay. This will be 7 points on the of the homework, so 70% of the homework. The second part then will be word 3 subsequent points. Good. Okay, well with that then, I will stop talking. You can use the last 20 minutes of class to start on homework number 4 as it is, and as questions come up, I'll definitely give you a hand, so. Good. And I'll say this with